Hello and welcome to this video about heterocyclic chemistry. Here we'll be looking at the aromaticity of heterocycles, but first we're going to have a recap by looking at aromaticity in benzene. Benzene is a 6-carbon cyclic molecule that has aromatic stabilization. If we look at the bonding, then each of the 6 carbon atoms is sp2 hybridized, which means that it takes its 2s orbital and mixes it with 2 of the 2p orbitals, and these overlap to form the sigma bonds which make the framework in the plane of the molecule. This leaves 6p orbitals perpendicular above and below this framework. Now, if we have 6p orbitals, they can be combined in 6 different ways. If we rank these according to energy, so that the most bonding interactions where all of the orbitals overlap with their neighbours at the bottom, and the most anti-bonding where each of the orbitals is out of phase with its neighbour at the top. Now if we fill these orbitals with 6 electrons, so 2 in each of the lowest energy ones, we end up with a stabilised aromatic system. And we can summarise these by looking at Huckel's rules. So for an aromatic system, it must be flat, it must be cyclic, there must be contiguous and non-broken ring of p orbitals, and there must be 4n plus 2 electrons. So what happens if instead of benzene, we remove one of the CH's and replace it with a nitrogen? This is pyridine, and because now we've swapped that carbon for a nitrogen, what we have to consider is that the nitrogen is more electronegative than the carbon. What this means is the energy of the whole system, because nitrogen is more electronegative, is lowered. And this means that pyridine is a better electrophile because the low energy system is better at accepting electrons, but it's a worse nucleophile. The electrons in the system are lower in energy. We can continue this trend. If we add more and more electronegative atoms into the ring, we can see that the LUMOs and the HOMOs are both lowered with each additional nitrogen atom. So what happens with a 5-membered ring? Well, we can do the same analysis. This time we've got 5p orbitals that we can mix in 5 different ways. Again, we can range these with the most bonding at the bottom, where each of the orbitals is overlapping in phase with its neighbour, to the most anti-bonding at the top, where each of the orbitals is out of phase with its neighbour. Again, we need to find 6 electrons, but this time in cyclopentadienyl cation, we've got 2 electrons from each of the double bonds, plus the negative charge, which gives us another 2 electrons. However, when we switch over to something like furan, instead of an anion, we can use the oxygen lone pair. But because the oxygen lone pair is in the system, and lone pairs are high energy filled orbitals, it means the energy of the whole system is increased. This means that the aromatic system is now a worse electrophile, but a better nucleophile. So what happens when we mix these two effects? Well, if we look at the nitrogen series of 5-membered heterocycles, we can see we start off with a high energy aromatic system, which contains the nitrogen lone pair. But as we add more nitrogens, again, the HOMO and the LUMOs are both lowered. So the first nitrogen increases the energy of the ring by using the high energy lone pair, but the subsequent nitrogens decrease the energy because they're electronegative. And in fact, if we go all the way down to tetrazole, which contains 4 electronegative atoms, we can see that this has effect on its properties. If we remove that proton from tetrazole, what we end up with is a negative charge on an aromatic ring that contains 4 electronegative atoms. This is a very stabilized negative charge, and that means that tetrazole is acidic. In fact, its pKa is around about 5, which means it's the same as acetic acid. What this means is you can actually replace acetic acid in things like drug molecules with tetrazoles. This has beneficial properties, and has been used in several drug molecules such as canderistan and lorcetin. So what happens in more complicated systems, which have heterocycles fused to different motifs? Well, we can apply the same concepts we've already seen to these systems. So in isoquinoline and quinoline, they're flat, they're cyclic, they are contiguous p orbitals, and they have 10, which is a 4n plus 2 amount of electrons. Here, the electrons are made up of each of the double bonds, but the ring contains an electronegative nitrogen atom, so it is more electron poor. In benzofuran, again, it is flat, it's cyclic, it's contiguous p orbitals, and it has 10 electrons, but this time to make our 10 electrons, we have to use the high energy oxygen lone pair. Now that makes that system electron rich. However, the effect is not distributed uniformly across the whole system. So in isoquinoline and quinoline, the pyridine, the nitrogen containing ring, is more electron poor than the carbon containing ring. Similarly, in benzofuran, the same as indoles and benzothiophene, the most electron-rich part is the heterocyclic ring, and the all-carbon ring is less electron-rich. So, in summary, heterocycles are aromatic if they satisfy Huckel's rules. Flat, contiguous p orbitals, cyclic, and 4n plus 2 electrons. However, in 6-membered heterocycles, we use an electronegative element to build the aromatic system, so these systems are electron poor. In 5-membered heterocycles, we use a high energy lone pair to build the aromatic system, so these are electron rich. These effects stack, such as the addition of extra electronegative atoms in a heterocycle makes the system more and more electron poor. We can apply the same rules to more complicated fused heterocycles, remembering that the effect is most pronounced on the heterocyclic ring in that molecule. Thank you for watching, and I'll see you next time.